Hi there, and welcome to this video on A-Level Chemistry for the AQA Specification, focusing on the topic of atomic structure and, in particular, electron configuration. Hi, I'm Manisha from StudyMind, where we help you to revise A-Level Chemistry with our helpful revision resources tailored to your subject, your specification, and to you. If you're new here, please make sure to click that subscribe button, and whilst you're watching, please leave any comments down below about anything you're unsure of. If it's your first time watching, make sure to let us know so we can send you our free revision resources. We also have helpful timestamps to guide you through the video. So, let's get started. Welcome to lesson 3 of 3 in this tutorial, Electron Configuration. In this tutorial, we'll be looking a lot more closely at the configuration of electrons, one of the smallest subatomic particles. Let's quickly recap what we learnt last time. We met two very important definitions, mass number and atomic number, plus we also looked at how to use them in calculations. Another one of our key learning objectives last time was to look at time-of-flight mass spectrometry. In this tutorial, we'll be covering the following key learning objectives. Firstly, we'll look at electron shells and subshells. We'll then move on to look at electron notations and electron configuration. Our last two learning objectives will cover the periodic table and ionization energies. Here are the three key specification points we'll be covering in this tutorial. Make sure to pause the video now and have a read through them before we begin. First, we'll be looking at the role of subshells. Here, we can see a visual representation of electrons. Electrons will move in electron shells around a central nucleus. The electrons will be found in different shells, which represent specific energy levels. Each electron is going to have a fixed energy. The shells will each have different energy levels. Since the electrons are found inside these shells, this means that electrons in different shells must have different energy levels. Shell 1 will have its own energy level, whilst Shell 2 and Shell 3 will also have their own energy levels. Each electron shell has a particular energy, and electrons can only have one of the fixed energy levels of the shells. The fixed energy of an electron is the amount of energy needed to move the electrons from one energy level to another. For example, here there is a certain amount of energy needed to move the electron from the second subshell to the third subshell. The energy level of the electron shells increases as the distance from the nucleus increases. This means that there's decreased interaction with the nucleus. An electron shell that is further away from the nucleus is going to have a higher energy level. As we go down from shell 1 to 2 to 3, we'll be increasing in energy. Each electron shell has something called a principal quantum number. The shell closest to the nucleus has quantum number 1. The second shell has quantum number 2, and so on. So the further away a shell is from the nucleus, the higher the principal quantum number. We're now going to cover some key definitions in this section. The first is a subshell. The other one is for orbitals. A subshell is one or more orbitals in the same shell which have both the same energy levels. We learnt that electrons are split into shells, each with their own energy levels. Well, electrons in each shell can be further split into mini subshells. This means that the electrons in the same shell do not all have the same energy level. There are 4 different subshells that we're going to cover: S, P, D, and F. This is a simple mnemonic to help you remember the 4 different shells. Some people do fencing. We've just seen that there are 4 different energy levels. We've just seen that there are 4 different subshells: S, P, D, and F. This means that not all the electrons in the same shell will have the same energy level. Therefore, in shell 1, there's only one S subshell. This means that all the electrons in subshell 1 will have the exact same energy level. Shell 2 is slightly different in the fact that it has an S and a P subshell. This means that some electrons will have more energy than others. Similarly, the third shell will have S, P, and D subshells. This means that there are 3 energy levels within this shell. The subshells can be thought of as the different stairs in one staircase. Electrons can have different energy shells, which would be the floor levels, and within each shell there's a different energy level, which would be the different stairs. The lower subshells are closer to the nucleus. Within each shell, we can have multiple subshells. The subshell S has the lowest energy because it contains the electrons that are closest to the nucleus. This means that in the third shell, the 3s subshell is going to have the lowest energy because it contains the electrons that will be closest to the nucleus. The 3d subshell will have the highest energy since it is the furthest from the nucleus. As the quantum number increases, the energy difference between the successive subshells will decrease. For example, the 4s subshell will have a lower energy level than 3d. As we move to shells with higher quantum numbers, which will get further away from the nucleus, the subshells will begin to overlap. The energy gap between the successive subshells will get smaller and smaller. Although subshell 3d has a higher energy level than subshell 4s, the overall energy level will be lower than shell 4. Each subshell will hold a specific number of electrons. In each subshell, the electrons will be held in orbitals. We'll be looking at these more closely. Each of the orbitals will hold 2 electrons, and each subshell will have a variable number of orbitals. For example, the s subshells will have 1 orbital, so they can hold up to 2 electrons. However, the f subshells will have 7 orbitals, therefore they can hold up to 14 electrons. We're now going to fill in this table, which shows the properties of each type of subshell. We'll be looking at how many electrons can fit into the orbitals of each of the 4 subtypes. We'll start off with subshell S. The total number of orbitals will be 1, which means that the maximum number of electrons will be 2. Our next subshell is going to be subshell P. The total number of orbitals will be 3, so the maximum number of electrons must be 6. Our next subshell will be subshell D. Our total number of orbitals will be 5, which means the maximum number of electrons is 10. Finally, we'll come to the F subshell. Our total number of orbitals is 7, and our maximum number of electrons must therefore be 14. Using the information in this table, we were able to calculate the number of electrons that each shell was able to hold. We know that each shell will hold a specific number of electrons. We'll now fill in this table. In our first shell, we're going to have 1s subshell. This means that we'll have 1 orbital and 2 electrons. The total number of electrons will be 2. In our second shell, we're going to have a 2s subshell and a 2p subshell. This means that we'll have in the s subshell 1 orbital, which is 2 electrons, and in the p subshell we'll have 3 orbitals, which is 6 electrons. This means our total number of electrons will be 8. Finally, in our third subshell, we'll have a 3s, a 3p, and a 3d subshell. Similar to before, in our s subshell we'll have 1 orbital holding 2 electrons. We'll have a p orbital holding 3 and 6 electrons, and a d subshell, which is going to have 5 orbitals, which gives us 10 electrons. Our total number of electrons, therefore, will be 18. We're now going to quickly summarise what we've just covered. In our first subshell, we'll have 1 subshell. In our second shell, we'll have 2. In our third, we'll have 3. In our fourth, we'll have 4. Now let's look at the number of orbitals in each subshell. In our first one, we'll have 1. In our p subshell, we'll have 3 orbitals, whilst in d we will have 5, and in f we will have 7. These 2 tables will be very handy in your revision, so make a quick note of them now before we move on. Inside an orbital
is the most likely place we'll find an electron. Each orbital can only contain a maximum of 2 electrons. These will spin in opposite directions. As electrons spin on their axes, the moving charge will result in the formation of a magnetic field. In each orbital, one electron will spin upwards, whilst the other one spins down. Whilst the different energy shells will have different energy levels, and different subshells will have different energy levels, the orbitals within the same subshell will have the same energy level. You need to understand subshell notation as shown in the diagram. Here, this arrow pointing to the number 1 will be the energy level. The arrow pointing to the type of orbital is the arrow pointing to S. Finally, the arrow pointing to the number 2 is showing us the number of electrons in each orbital. Within each subshell, we can draw out the electrons in orbitals. Each box will represent one orbital. The electrons are represented by the arrows inside the boxes. The arrows will always point in opposite directions to indicate that the electrons are spinning in opposite directions. This diagram helps us to understand orbitals and subshells. We'll be looking at nitrogen in this example. We've just seen that each box represents an orbital, and each of the arrows represents an electron. In shell 1, there's a 1s orbital. This contains 2 electrons spinning in opposite directions, hence the opposite arrows. In shell 2, there are 2 subshells, the 2s one and the 2p. In the s subshell, there are 2 electrons, whilst in the p subshell, there are 3, each in separate orbitals. In exams, you'll often have to write electron configurations for different elements. You can answer these questions by following the rules. The first rule is that electrons start filling up with the lowest energy subshells. Electrons will fill up the 1s subshell first, then the 2s, and then the 2p, and so on. There's one exception to this rule. The 4s subshell will fill up before the 3d subshell. Therefore, in electron configuration, 4s would be written before the 3d subshell. Despite the principal quantum number of 4s being larger, this is overridden by the lower energy level of the 4s subshell, meaning that it is filled first. We're now going to fill in this table. Pause the video now to have a go at this yourself before we begin. We'll start off with helium. We know that in helium the total number of electrons will be 2. The subshell that they're in would be written 1s2. Similarly, lithium is going to have 3 electrons. We would write this as 1s2, 2s1. element is nitrogen. This has got 7 electrons, which would be written as 1s2, 2s2, 2p3. Finally, we'll look at calcium. This has got 20 electrons. This would be written 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Helium has 2 electrons. There's only one s subshell in shell 1. Therefore, the 2 electrons will fit into this, and we do not need to use shell 2. The rest of the explanations are given on screen here. Pause the video now to have a read through them so you know what's going on. Before they start pairing and sharing an orbital with another electron, electrons will fill each orbital in each shell individually. We're trying to avoid having pairs of orbitals. Having 2 electrons in a single orbital will require more energy, as energy is needed to overcome the repulsion between the electrons. Let's consider nitrogen, which has 7 electrons. First, 1s2 and 2s2 are filled up with 2 electrons each, leaving 3 electrons for the 2p subshell. P subshells will contain 3 orbitals. 1 electron in each orbital is filled, rather than putting 2 electrons into a single orbital. As we can see here, on the left is a correct example, whilst on the right is the incorrect version. Imagine 3 hotel floors, 1s, 2s and 2p. We have 7 guests staying, which would be the electrons. Floors 1 and 2s will have 1 room each, whilst floor 2p has 3 rooms. Each room can contain 2 guests maximum. We fill up floor by floor, and when we reach floor 2p, we would rather give each guest their own room by using 3 rooms, each with 1 guest, rather than using 2 rooms. One of the most important things to remember about drawing electron diagrams is to draw the electrons as arrows, pointing in opposite directions. Now let's look at how we find the electron configuration of ions from either the S and the P block of the periodic table. We know that the electrons are eliminated from or added to the subshell with the highest energy. Now let's look at how we would work this out. First, we need to take the electron configuration of the element. Then, we simply add or remove electrons from the subshell with the highest energy. If it's a negative ion, we will add electrons. If it's a positive ion, we will remove electrons. Now let's go through some examples. We'll start with calcium. Calcium makes a positive ion. In doing this, 2 electrons are removed from the 4s subshell. This is shown here. Another example is fluorine, which forms a negative ion. For this, we add an electron to the highest energy subshell. Again, is shown here. In some textbooks, you might see noble gas symbols being used. For example, potassium could be written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, or more simply, we could just write AR 4s1. A half-full or full 3D subshell is especially stable. Chromium and copper will have unusual properties as their subshells fill differently to usual. We'll fill in this table to look at their configurations. We'll start off with chromium. The expected configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. We'll fill in this table to look at their configurations. For chromium, we would expect the configuration to be as follows. However, the actual configuration is slightly different. Similarly, for copper, this is the expected configuration. The actual configuration is shown here. From these examples, we can see that a half-full or full 3D subshell is especially stable. Usually, when atoms form ions, they lose electrons from the 3D subshell first, and then the 4s subshell, as the 3D subshell is at a higher energy level. However, transition metals will lose electrons from the 4s shell first. We'll now look at the difference between a chromium atom and a chromium ion. Let's look at the atom first. This will have a charge of 0 since it's an atom. Its electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. We'll now look at the chromium ion. This has a charge of +3. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. The electron structure will define an electron's chemical properties. Therefore, the structure is responsible for how an element behaves chemically. As we've seen before, forming ions will involve the transfer of electrons. Elements in the same group are very similar. They will have the same number of outer electrons, and therefore they will have extremely similar chemical properties. This is shown across the top of the periodic table. Elements in the same period will also be quite similar. These will have the same number of shells, and therefore, again, will have similar chemical properties. These are shown down the left-hand side of the periodic table. This figure allows you to identify which element is found in which block of the periodic table. The periodic table is broken up into 3 different blocks: the S block, the D block, and the P block. S block elements will have 1 or 2 electrons in their outermost shell, resulting in a configuration of S1 or S2. The electrons of S block elements are lost very easily to form positive ions, and therefore S block elements are very reactive. The elements will also conduct electricity since they'll have delocalized electrons. The P block elements will have 5, 6 or 7 electrons in their outermost shell, so they gain ions to form negative ions. So they gain electrons to form negative ions. Elements can also share bonds. Elements can also share electrons to form covalent bonds. The D block elements have an outer shell configuration between S2p6 3d1 and S2p6 3d10. They are often called transition metals. They will lose electrons from their S and D subshells, forming positive ions in metallic structures. Inert gases are found on group 0, and they have an S and P subshell that are full. These are inert because they do not transfer electrons. Let's fill in the table row by row. Firstly, we'll look at the S block elements. These will be groups 1 to 2, and the type of bonding they exhibit will be ionic. Next, we'll look at the D block elements. In the P block, they have groups 5 to 7, and they exhibit covalent bonding. Next, we'll look at the D block. These are the transition metals, which exhibit metallic bonding. Finally, we'll look at the inert gases. These are in group 0, and they're unreactive. Now that we've been through the table together, have a go at filling it in yourself. This is a useful revision tool to help you remember the information we've just learnt in this section. When the S block elements form positive ions, the ions will have the same electron configuration as that of an inert gas. When potassium loses an electron, it will have the same properties as argon. When the P block elements form negative ions, the ions formed will have the same electron configuration as that of an inert gas again. This is shown in the following example with nitrogen. We'll now move on to the next specification point, covering relative charge and relative mass. We'll now move on to the next specification point, looking at ionisation energy. Ionisation is a process by which an electron is removed from an atom or molecule. This process is known as being endothermic. This is because energy is required to break the force of attraction between the electron and the central positive nucleus. Electrons will move in electron shells around the central nucleus. They'll be attracted to the positive nucleus. The different shells will represent specific energy levels. If we try to remove an electron, this is known as ionisation. We'll now look at the two definitions to do with ionisation energies. There are different kinds of ionisation energies, including the first, second, and successive ionisation energies. The first ionisation energy is the energy needed to remove one electron from each atom of an element in 1 mole of gaseous atoms to form 1 mole of gaseous ions with a 1+ charge. This is shown here, where 1 electron has been removed from xenon gas. We'll now see this in pictorial form. Here, 1 electron is being removed. This results in a positive xenon ion. The second ionisation energy is the energy needed to remove 1 electron from each ion of an element in 1 mole of gaseous 1+ ions to form 1 mole of gaseous ions with a +2 charge. Again, this is shown with the gaseous xenon ions in this equation. The only difference is that here we are starting off with a positive xenon ion, and we are removing another electron from it. This results in a gaseous 2+ ion. The successive ionisation energy is the energy each time you remove an electron. When talking about successive ionisation energies, we often draw a graph for a particular element of the first ionisation energy, second ionisation energy, third ionisation energy, and so on. This is an example of what the equation would look like. Try substituting in various numbers to see how this would work. It's really important to take note of the state symbols in ionisation energy questions. The gas state symbol is used because gaseous atoms are used when ionisation energies are recorded. Here, we can see that 1 mole of atoms is going to be converted into 1 mole of ions. Remember, we are removing 1 whole mole of electrons from a mole of atoms to form a mole of positive ions. This means that it's really important you remember to use the term 1 mole of atoms in your definition. The higher the ionisation energy, the more difficult it is for an atom to lose electrons to form an ion. This means that more energy is required to remove it. Here are some more key definitions to do with ionisation energy. We'll be looking at the definition of a period, a group, shielding, and nuclear. A period in the periodic table is a horizontal row, as highlighted here in blue. All the elements in a period will have the same number of electron shells. A group in the periodic table is a vertical column, again highlighted in the picture here. All the elements in a group will have the same outermost number of electrons. The shielding effect is the effect of the inner electrons. This will reduce the pull of the nucleus on the electrons in the outer shell. The nuclear charge is a measure of how positive the nucleus is. The higher the atomic number of an element, the more protons it has in its nucleus, and hence a higher nuclear charge. The effective nuclear charge is the net positive charge experienced by the outermost electron from the nucleus. It's less than the nuclear charge because it takes into account the repulsion from inner electrons, which provide a shielding effect, and also the attraction from the positive nucleus. The size of the ionization energy is determined by the strength of attraction between the outer shell of electrons and the central nucleus. The stronger the attraction, the harder it is to remove the electron, and the higher the ionization energy. We'll now look at the following factors which determine the strength of attraction between the nucleus and outer electrons. First, we'll look at atomic radius, then nuclear charge, and finally the number of inner shells. The higher the atomic radius, the lower the ionization energy will be. The outer electrons will be further from the nucleus. However, this means that the attractive pull from the nucleus is lower. The higher the nuclear charge, the higher the ionization energy will be. This is because the greater the positive charge of the nucleus, the stronger the attraction for the outer electrons. The more inner shells we have present, the lower the ionization energy will be. By inner shells, we mean the shells between the outer shell and the nucleus. For example, if the outer electron is in shell 4, then there are 3 inner shells to repel the outer electrons, lessening the pull towards the nucleus. This effect is known as shielding. Let's look at neon and argon. Which of these has got the higher ionization energy? We'll consider the properties one by one. Neon will have a higher atomic radius than argon, but a lower nuclear charge. Argon will have more inner shells, which means that the electrons are more shielded from the nucleus. Overall, neon will have a higher first ionization energy compared to argon, due to it having less shielding. Pause the video now to have a go at this one on your own. Zinc has a higher atomic radius and more inner shells than sodium, so has a lower ionization energy. This is despite the fact that zinc has more electrons in its nucleus than sodium, so there is a greater nuclear charge. The first 2 factors, however, will override the nuclear charge. Students often get confused by nuclear charge. It is not a measure of overall charge, but instead of the charge of the nucleus, which is determined by the number of protons. A sodium atom has a lower nuclear charge than a zinc atom, even though both are atoms and not ions. Hence, they both have an overall charge of 0. We'll now move on to the final specification point. Every time there is a sudden jump in ionization energy, we can tell that another shell has been entered. This means that more and more electrons will be removed, each from an ion that is becoming increasingly positive. Here, we can see the successive ionization energies of argon. We can look at successive ionization energies to understand shell structure. Successive ionization energy will increase between the shells. Every time a new shell is broken into, there will be a sudden rise in ionization energy. As shown here, even if we haven't broken into a new inner shell, the ionization energy will increase because you are removing the electron from an increasingly positive ion. Each time an electron is removed, the ionization energy will keep increasing. This is because, as we've just seen, the electron is being removed from an increasingly positive ion. To recap, first ionization energy is the energy needed to remove one electron from each atom of an element in 1 mole of gaseous atoms to form 1 mole of gaseous ions with a +1 charge. Ionization energy is defined as removing one electron and moving it an infinite distance away. When you remove the electron, it is attracted back to the positive ion. The second ionization energy will be a higher value than the first ionization energy. This is because when the second electron is removed, it is attracted back more because the ion has a higher charge. As an electron is moved away from a positive ion, it's attracted back towards it. Therefore, as the ion increases in positivity, larger amounts of energy will be needed to remove the electrons from it. For example, moving an electron away from the 2+ ion is a lot more difficult than removing it from the 1+ ion shown on the left. Every time there is a sudden jump in ionization energy, we can tell that another shell has been entered. In this diagram, we can see that there is 1 electron in the outer shell, and then 8 electrons in the next inner shell, and so on. You can also find out which group of the periodic table the element belongs to. We can do this by counting how many electrons are removed before the first sudden rise in ionization energy. For this diagram, we can tell that it is a group 1 element, as it has 1 outer electron. According to the graph for sodium, there is 1 electron removed before the first sudden rise, 8 before the next rise, and finally 1 electron. Here, we're going to fill in the table to show this. In our first shell, we're going to have 2 electrons. In our second shell, we're going to have 8 electrons. And finally, in our third shell, we're just going to have 1. A few slides ago, we looked at the trends in successive ionization energies. We can also look at trends in the first ionization energies across a period and down a group. This is a recap of ionization energy on the screen now. We're going to consider the trends in ionization energy both down a group and across a period. The first ionization energy will decrease down a group due to 2 main factors. These are the atomic radius and the shielding effect. The atomic radius will increase as you go down a group in the periodic table, because an extra shell is added each time. This will decrease the ionization energy. There is also an increase in the number of shielding electrons. Again, this will decrease the ionization energy. However, there is an increase in the nuclear charge as you go down a group. This will increase the ionization energy, but this effect is outweighed by both the increase in the atomic radius and the increase in the shielding. The atomic radius will increase as you go down the group in a periodic table. As you go down the group, an extra electron shell is added each time, so the distance between the nucleus and the outermost electron will increase. The shielding effect will also increase as you go down the group. As an extra electron is added each time you go down the group, the number of inner electron shells will increase. However, Contrary to the other two, the nuclear charge will increase down the group, but the two factors shown just above it will outweigh this. If an AQA exam asks you to explain why ionisation energies increase down a group, mention that the atomic radius and the shielding factors will override the nuclear charge. Don't just mention the first two factors, make sure you mention that they are outweighed and that you mention nuclear charge. If an AQA exam question asks you to explain why ionisation energies increase down a specific group, pick out certain elements. For example, if they ask about group 1, then explain as you move from lithium to sodium, there is an increase in the atomic radius and an increase in shielding. First ionisation energy will increase across a period. This is due to two factors: nuclear charge and atomic radius. The atomic radius will decrease slightly as you go across a period. This is a subtle decrease. The nuclear charge of the nucleus will increase. The nucleus will pull the outer electrons closer to it, which decreases the atomic radius. There is no change in the shielding effect across a period. All the electrons within the same electron shell are around the same energy level. Electrons are being added to the same outer shell as you go across a period. As we've just seen, the atomic radius will decrease across the period, resulting in an increased ionisation energy. There is no change in the shielding effect across the period, as discussed in the previous slide. Again, the nuclear charge will increase, resulting in an increased ionisation energy once more. If an AQA exam question asks you to explain why ionisation energies increase across a period, then please remember to mention all three factors, including the shielding effect. Nuclear charge will increase, but the shielding effect will stay constant. This means that the effective nuclear charge will increase. We can see that this graph shows us the trends in ionisation energies across a period. The graph on the previous page was not a perfectly straight line, which means that there are a couple of exceptions to the trends across a period. Firstly, there is a drop in the first ionisation energy between group 2 and group 3 elements. For example, if we take beryllium in group 2 and boron from group 3, we would expect the first ionisation energy of beryllium to be higher than that of boron, due to the increased nuclear charge and the decreased atomic radius. Boron's outer electron will be in the 2p subshell. This means that it's at a higher energy level. It's therefore found further away from the nucleus and experiences more shielding from the inner electrons. These two factors will override the effect of an increased number of protons in the nucleus. This means that there is a lower first ionisation energy of boron compared to beryllium. Let's fill in the table to show why. We'll start off by looking at beryllium. This has got 4 outer electrons, and its configuration is 1s2, 2s2. Its first ionisation energy measures at plus 900 kilojoules per mole. We'll now fill in the same data for boron. This has got 5 electrons, and the configuration would be 1s2, 2s2, 2p1. Its first ionisation energy is only 799 kilojoules per mole. The change in the usual pattern of ionisation energies can only be proven by the presence of subshells. There is also a drop in the first ionisation energy between the group 5 and group 6 elements. On this occasion, the outer electrons are in the same subshell for both elements, the 2p subshell, so there's very little difference in the atomic radius or shielding. For example, let's compare nitrogen and oxygen. We'll fill in the data for nitrogen first. The number of outer electrons is 7, so the configuration would be 1s2, 2s2, 2p3. The first ionisation energy would be plus 14,000. Now, let's fill in the same data for oxygen. This has got 8 electrons, and its configuration would be 1s2, 2s2, 2p4. Its ionisation energy would be plus 1314, which is lower than nitrogen. In nitrogen, there is only 1 electron in each orbital. In oxygen, there are 2 orbitals with 1 electron each, and 1 orbital with 2 electrons. There is always more repulsion between a pair of electrons within an orbital. We've now covered all the learning objectives in this section.
If you liked this video, make sure to catch our latest videos by subscribing down below and leaving a comment on a topic that you'd like to see a video on. Click here to watch more videos on our series of A-Level Chemistry, or visit our website studymind.co.uk for past paper compilations by topic and specification.